Good morning, students. So this is the second lecture on chapter 2. If you remember, we started chapter 2 in the last lecture. We went over a couple of topics. So today, in today's lecture, we are talking about position vectors and force vectors. Okay, so if you remember, we talked about scalars, we talked about vectors, we talked about Cartesian notation in two-dimensional space. All right, so now we'll be talking about 3D space, Cartesian form or Cartesian system in 3D space. Okay, so first of all, how to represent a position vector in Cartesian coordinate form from the given geometry. And then represent a force vector directed along a line. Okay, so we'll move ahead and we'll see what do we mean. All right, so first of all, the question is, what is a position vector? All right, so a position vector is a vector which gives you the direction of one point with respect to the other point. Right? If you look at this this figure on the screen, so we have this point A and we have this point B. Right? Here, this is point B. This is point A. Right? Now this small r, we represent the position vector by small r. So this small r gives you the position vector from point A to point B or from point B to point A. So if we say RAB, it means the position vector from point A to point B. Or if we write RBA, it means position vector from point B to point A. And just remember that RAB is not equal to RBA. Right? And then we have this guy U. We know what is U, right? Small u. It's a unit vector giving us the direction, right? So we'll talk about this. Okay. So this was just the introduction about the position vector. Now let's jump on to the lecture and let's see how do you find the position vector. So as we discussed earlier, a position vector is defined as a fixed vector that locates a point in space relative to another point, right? So we already said that, right? Position vector gives you the position of one point with respect to the other point, right? So that's what this statement means, right? Now, if you look at this 3D box, again, this is a 3D box, right? You have x-axis, you have y-axis, you have z-axis, right? Because we are dealing with three-dimensional space. Okay, so we have this x, y, z-axis as our coordinate axis. Then we have this is our point A, and this is point B, right? This is point B. This is point A. Okay. Now let's talk about the position vector, right? So this blue line with an arrow gives you the position vector small r, right? So again, once we talk about RAB, which it means that position vector from point A towards point B, right? And again, we need to remember that RAB is not equal to RBA. Okay. Now, for the moment, let's talk about RAB, right? So how do we get RAB or position vector from point A to point B? Always remember, we go from tip to tail, right? Tip to tail. So we also call it tip to tail rule, okay? Now, we have some coordinates of point A, right? Let's call them XA, YA, and ZA along X, Y, and Z coordinates, right? And we have three coordinates of point B. Let's call them XB, YB, and ZB, again, along the X, Y, Z coordinates, okay? So we have three coordinates of point A and three coordinates of point B. Now, in this position vector, as we are talking about RAB, so A is the starting point, B is the finishing point, or we are going from A to B. So B is the tip and A is the tail. So as we say that we'll use the tip to tail rule, so we need to subtract the coordinates of point A from point B, right? So point B minus point A, we can just say in simple terms, right? So what we'll do XB minus XA, YB minus YA, ZB minus ZA. This will give us the coordinates of position vector, right? Along with IJK, if we write IJK with these coordinates of position vector, that will be the position vector RAB in Cartesian vector form. Okay, now let's move forward and let's see. So we already talked about that we have these 2 points A and B in this 3D system. The coordinates, let's call them XA, YA, and ZA. For point A, these are the coordinates, and for point B, we have XB, YB, and ZB, right? So once we have these, then how do we find the position vector? Position vector RAB, R sub AB, which is the position vector directed from point A to point B, right? So how do we get that? We get that by this equation. As we already discussed, R sub AB equals XB minus XA times I plus YB minus YA times J plus ZB minus ZA times K. And of course, we have these units because everything is in meters, so we'll have unit of meters or feet or inches, anything, right? Which is according to the system. Okay. So please note that B is the ending point and A is the starting point. We already know that. Always subtract the tail coordinates from the tip coordinates, right? As we said, that tip to tail rule, right? So tip minus tail, B minus A. That's why we have XB minus XA, YB minus YA, and ZB minus ZA, right? Along with IJK, which gives us the Cartesian vector form. Okay. So B is the tip and A is the tail, B minus A or tip minus tail. Okay. So always remember, whenever you are determining the position vector from one point to the other point, always use tip to tail rule, right? And always remember that RAB is not equal to RBA, right? Okay. Let's move forward. Now, section 2.8 of your book, force vector directed along a line. So let's look at that. What is a force vector directed along a line? Now, in this system, this is a given system. There is some hook here at point A. There's a cable or a rope from point A to point B, and there's a force F applied at point B, right? Along the direction of the cable AB. Okay. All right. So if a force is directed along a line, then we can represent the force vector in Cartesian coordinates by using a unit vector and the force's magnitude. Okay. So we have this force. We know that we can find out this small r, position vector, and we can also find this small u, which is the position vector for the direction of this force vector F, or we can say the line AB. Okay. All right. So let's move forward. How do we do that? First of all, we'll find the position vector RAB. Right. So we'll find this guy, which is the position vector from point A to point B. Okay. We know how to do that, right? XB minus XA, YB minus YA, ZB minus ZA, along with IJK notations, we'll get the position vector R sub AB, right? We'll get this guy, okay? So by now we know how to get this guy, okay? Next step, find the unit vector describing the line's direction, okay? So we'll take on this guy, we'll determine this small u, which is the position vector. Now again, this UAB is the position vector for line AB, or from A towards B, right? So UAB, how do we get UAB? We use this equation for UAB, right? RAB divided by magnitude of RAB, right? So we already know that how to get the unit vector. That's the vector divided by the magnitude, right? So what is the vector? Vector is RAB, is a position vector, right? Divided by RAB, which is the magnitude, right? So this guy RAB is the vector, and this guy RAB, this is the magnitude. So that's how we get this unit vector U sub AB. Okay. So now from the first two steps, we have RAB, which is the position vector from A to B, and we also have U sub AB, which is the unit vector, right? Now multiply the unit vector by the magnitude of the force. So we can use this, we can do this to find the force vector F, right? In Cartesian form. So how we do that? F times UAB. F is the magnitude. This guy, this is the magnitude, and this UAB is the position vector. We already know that it's a vector. Okay. So once we do that, we'll get the force vector in Cartesian form. Okay. Now let's move forward and let's do an example. All right, so what's the given system? If you look at this given system, again, we have a 3D system. So we have three-dimensional space. We have three axes, three coordinate axes. So we have x-axis, y-axis, z-axis. Right? Now what is given? 420 Newton force along the cable AC. Okay, so we are talking about this force, let's say F sub C, which is 420 newtons, right? Shown by this black arrow, okay? Along the line AC or cable AC, okay? And what do we need to find? We need to find the force F sub AC in Cartesian vector form, right? So we can use the knowledge, the concept which we just learned in the last couple of slides to find this FAC in Cartesian vector form, okay? So let's see how we do it, okay? What are the steps? First of all, we know that we need to find the position vector RAC, right? So we'll find out, we'll determine this position vector RAC, R sub AC, right? Again, how do we find the position vector? Tip minus tail rule, right? So coordinates of point C minus coordinates of point A, along with I, J, and K. So we'll get the position vector in Cartesian form, or we'll get this R sub AC, okay, in vector form. Then we'll find out the unit vector UAC, right? So UAC is RAC vector divided by the magnitude of RAC, okay? So we'll get this unit vector or U sub AC. Next step, we'll find out the force vector FAC in Cartesian form, right? We'll do that here. FAC equals F times UAC, okay? So F is 420 newtons times UAC, which we were finding out here in the first step, okay? So that's how we'll find out this FAC in Cartesian form. All right, so let's move forward and let's see how we do it, okay? So now, first of all, first step was to find out the position vector R sub AC, okay? So we have the geometry given in this diagram, and we have X, Y, and Z axis. This is our X axis, this is our Y axis, and this is our Z axis, right? This is point C, this is point A, right? This is point C, this is point A. Okay, so now to find out the position vector, we know we need to subtract the use the tip to tail rule and subtract the coordinates of point A from point C. Okay, so this is your RAC, right? XB minus XA or XC minus XA. So what is XC? If you look here, XC is 2, right? 2 meters. And XA is 0. So XC minus XA will get 2 times I, right? Then for Y coordinate, we'll do YC minus YA. So what is YC here? YC is 3 meters, right? And what is YA? YA is 0. So 3 minus 0, we'll get 3 times J. Okay. Then we'll talk about the Z coordinate. So ZC minus ZA. Right now, ZC is -6, right? Because it is towards the negative x direction. Oh, sorry. ZC is 0, right? ZC is here, so it's 0 because it's at the origin. Okay, and ZA is 6, right? It's in the positive Z direction, so it's positive 6. So ZC minus ZA will give us 0 minus 6. So we'll get a -6 times K. And of course, the unit of meters. So that's how we found the position vector R sub AC. Okay. Now let's move forward. This is the same what we did, right? Subtracting the coordinates of point A from the coordinates of point C, right? So that's what we did. XC minus XA, YC minus YA, and ZC minus ZA. And of course, the unit of meters. Okay. Now, after we have this, we have the position vector RAC. Now we need the magnitude of position vector RAC, or we need this guy, right? RAC, magnitude. So how do we get the magnitude? X squared plus Y squared plus Z squared whole square root, right? So we will use this to find out the magnitude of position vector, RAC, okay? So 2 squared plus 3 squared plus -6 squared whole square root, we get 7 meters as the magnitude of this position vector. Okay. So now we have the position vector RAC. We also have the magnitude of that position vector RAC, right? Okay, what next? We already discussed in the last couple of slides that next we'll find out the unit vector, right? So let's find out the unit vector, UAC, okay? And what is UAC? UAC is the position vector divided by the magnitude of position vector, right? So we do like this, position vector RAC divided by the magnitude of RAC, okay? So we already know RAC, we already know the magnitude of RAC, so we can find out the unit vector. And then once we have the unit vector, then we can find out the force vector FAC in Cartesian form, right? Which will be F, a force, times the unit vector U sub AC, okay? So if you just put in the value of UAC here, you'll get this guy, 420 times UAC, or the position vector divided by the magnitude of position vector, right? So if you just put in the values, you'll get this. 420 is the force, 420 newtons, times RAC. So we have this vector. This is your position vector 2I plus 3J -6K divided by 7. All right. So divide by 7, which is the magnitude of position vector. Now meters cancel out for the this unit vector, right? UAC. So we'll get newtons for the force again, right? So then we get FAC in this form. So this is the final form of FAC in Cartesian vector form. Okay, so 120I plus 180J negative 360K newtons. So this is your force vector in Cartesian form. Okay, so that's how we implement or we apply the concepts which we just learned in today's lecture regarding the position vector, the magnitude of position vector, the unit vector, and the force vector directed along a line. All right, so that's how we do that. All right, so let's do another problem so that we are, we get more practice to do such kind of problems. Okay, and we are better prepared for the homework and for the test. All right, so let's see the system here. Okay, there's a flagpole. Okay, this is point A, this is point C, this is point B. All right, then we have this x-axis, y-axis, and z-axis. Okay, so there's a 3D system, 3D space system. Okay, and we have these two forces acting at point A, right? FB and FC. All right, so let's come back to the statement. What is given? Two forces are acting on a flagpole. As shown in the figure, FB equals 560 newtons, FC equals 700 newtons. Okay, so we have these two forces acting at point A on this flagpole. Now, what we need to do? We need to find the magnitude and the coordinate direction angles of the resultant force. All right, so we need to find the resultant force, right? The magnitude and the angles. Okay, so if you remember, in 3D space, we use alpha, beta, and gamma, three angles, right? And we need to find the resultant force also. Okay, all right. So what we need to do? What are the steps? So first, we need to find the forces along AB and AC in Cartesian vector form, right? Because we cannot just add FB and FC. We need to convert them into Cartesian vector form, right? So that we can add them. So after we have these FAB and FAC in Cartesian form, then we can add these two forces to get the resultant force FR. Okay, and after that, once we have that FR, then we can determine the magnitude and coordinate angles of that resultant force FR. Okay, so we have the geometry given, we have the distances, we have the coordinates. So now we can go ahead and find out this FAB and FAC, right, in Cartesian form. Okay, let's move forward. Okay. Now, to find out the FAB and FAC, the two force vectors in Cartesian form, what we need? Right, we just did one problem, right, and we learned the concept before that. So what we need the position vector, we need the magnitude of position vector, and we need the unit vector. Only then we can find the force vector in Cartesian form, right? So we need this guy, RAB, we need this guy, RAC, we need the magnitude of RAB, and the magnitude of RAC. Okay, now let's talk about RAB first. Okay, RAB is the position vector from point A towards point B, right? So this is your point A, this is your point B, right? So point A towards point B. Okay, So this is your position vector, and again we will use tip to tail rule. Don't forget tip to tail. All right, so here B is the tip, A is the tail, because we are finding out RAB, right? So A is the tail, B is the tip, and we always do tip minus tail. So coordinates of point B minus coordinates of point A, right? So XB minus XA, YB minus YA, and ZB minus ZA. Okay, so let's do that. Okay, so what is the X coordinate of point B? Right, X coordinate of point B, right? It's 2 meters, right? What is the X coordinate of point A? It's at the origin, so it's 0. So 2 minus 0, right? So we'll get 2I. Then let's talk about the Y coordinate. So YB, what is YB? Y coordinate of point B, right? So this is Y axis, right? So we have -3, right? Because point B is in the negative Y direction. So -3, and what is the Y coordinate of point A? Again, is point A is at the origin, so it's a 0. So -3 minus 0, we get a -3 times J. Now let's talk about the Z coordinate. Okay, so what is the Z coordinate of point B? Z coordinate of point B is 0, right? 0, and what is the Z coordinate of point A? Z coordinate of point A is in the positive Z direction, right, from the origin, so it's positive 6. So 0 minus 6, so we get a -6 times K, and of course unit of meters, because all the dimensions are in meters. Okay, so that's how you get this RAB. All right, similarly you can find out this RAC, right? Position vector from point A to point C, and here point C is the tip, point A is the tail. So again, tip to tail rule, tip minus tail, or the coordinates of point C minus coordinates of point A, right? So we'll get this guy, which is 3I plus 2J minus 6K meters. Okay, so that's how we found this RAB and RAC, which are the position vectors along AB and AC. All right. Okay, so we are done with the position vectors. Next, we want to find out the magnitudes of these position vectors. So let's find out the magnitudes of these position vectors. All right, so how do we find the magnitude of position vectors? Let's talk about RAB. We have the position vector RAB here. So we'll do x squared plus y squared plus z squared whole square root, right? So we'll do that here in this fashion. So 2 squared plus -3 squared plus -6 squared whole square root, right? So use your calculators and you get 7 meters as the magnitude of position vector RAB. Okay, and similarly, you'll find out this RAC, which is the position vector from A to C. So the magnitude is given by this equation, x squared plus y squared plus z squared whole square root, right? So 3 squared plus 2 squared plus -6 squared whole square root will again give us 7 meters. So this is just a coincidence that RAB equals RAC because of the given geometry, right? But it's not always like this. Okay, so don't take this that okay, RAB equals RAC. It's not, right? It's just that due to this given geometry, they are coming up equal. All right. Okay, so now we have the position vectors and we have the magnitude of these position vectors. Okay, so now let's move forward and find out the force vectors in Cartesian form. Okay, So first of all, let's find out FAB, right? The force vector along line AB. Okay, so we know that. How do we find it? FAB equals F times UAB. What is UAB? Unit vector equals the position vector divided by the magnitude of position vector, right? So RAB in vector form divided by magnitude of RAB, right? So this is the vector, this is the magnitude, right? Just remember always, this is the start of this course, so you need to remember that in these presentations, in these lectures, and in your book, red, italic, and bold is always a vector quantity, right? Okay, so this RAB in red is a vector, and RAB in a black is a scalar, which is the magnitude of RAB, right? Okay, so just put in the values. FB is 560 newtons, just put the value. RAB, the vector is 2I minus 3J minus 6K divided by 7, which is the magnitude of position vector. So what do we get? We get FAB in this form. FAB equals 160I negative 240J negative 480K in newtons. Always don't forget to write newtons. Sometimes I also forget to write down these units, but you don't have to forget the units because you'll lose points. Okay, so don't lose points. Okay, so I think by now we are clear how to find the position vector, how to find the magnitude of position vector, how to find the unit vector, and how to find the force vector in Cartesian form, right? Or we can say force vector directed along a line in Cartesian form. Okay. All right. So we are done with this part of the problem. We are done with finding out FAB in Cartesian form. Now let's move forward and let's find out FAC. Right. To find out FAC, we already have the force F, which is 700 newtons. We already have the position vector RAC, and we also have the magnitude of position vector RAC, right? So FAC, this guy, equals F, which is 700 newtons, times the unit vector UAC. UAC is RAC vector divided by magnitude RAC, right? And of course, newtons. Okay, just put in the values. 700 times 3I plus 2J minus 6K, which is the position vector RAC, divided by 7, which is the magnitude, and newtons. Okay, so just simplify this, and you'll get FAC equals 300I plus 200J negative 600K newtons. Okay, so until here, what we have done, we have found out FAB and FAC in Cartesian form, right? Now, if you remember what we were required to do in this problem, we were required to find the resultant force, right? So now we can just add FAB and FAC and find out the resultant force, right? So let's do that. Okay, so this is the resultant force, FR equals FAB plus FAC, right? So just if you go back, yeah. So just add the X, Y, and Z components, or I, J, and K components of FAB and FAC, right? So for FAB, 160I, for FAC, 300I, right? So 160I plus 300I. Then negative 240J plus 200J. Then negative 480K, negative 600K. So just add these three components and you'll get 460I, negative 40J, negative 1080K. always newtons. So this is your resultant force Fr. Okay. All right. So now you have the resultant force in Cartesian form. Now you can find out the magnitude of resultant force, right? So let's find this. Let's find Fr magnitude. Okay, so we know how to find the magnitude. What we do x squared plus y squared plus z squared, right? So we'll do 460 squared plus negative 40 squared plus negative 1080 squared, whole square root, right? So we'll get this guy 1174.6 newtons, or we can say 1175 newtons. So this 1175 newtons is the resultant force, or you can say the magnitude of resultant force Fr, right, which is the resultant of this Fb and Fc. All right. So with this method, we can find out the resultant of any number of forces, right? There are 2 forces or more, maybe 5 forces, 10 forces, 20 forces. You just need to find the forces in Cartesian form and then add those forces, right? So if you add those forces, you'll get the resultant force of all the forces. Okay. And again, if you remember, we talked about, I think in the last lecture, that why do we do this? Why do we want to find out the resultant force, right? Let's say in this case, we have 2 forces, Fb and Fc. If we want to, analyze this system or analyze this flagpole, if it is stable or it is failing, right? It is safe or it is unsafe, then we'll have to analyze this, right? So first we need to analyze with Fb, then we need to analyze with Fc, and even then we are nowhere, right? We don't know what is the total force, right? So that's why we want to find out the resultant force, and then we'll do just one analysis, and we'll do the analysis with this Fr of 1175 newtons, and we'll find out whether this flagpole is safe or not. All right. Okay. So there was another requirement of finding out the coordinate angles, right? We know that the coordinate angles with x, y, and z axis are alpha, beta, and gamma, right? Alpha with x-axis, beta with y-axis, and gamma with z-axis. So let's just find out these coordinate angles of this resultant force, right? So alpha equals cosine inverse 460 divided by 1175. What is 460? That is the x coordinate of a resultant force. This guy, 460, right? So we have 460 divided by 1175, which is Fr, right? So we get 66.9 degrees, which is your alpha, or the angle which Fr makes with the x-axis. Similarly, we get this beta as 92 degrees, but how do we get this? Y component of the resultant force divided by the resultant force. So negative 40 divided by 1175 will give you 92 degrees. So this is the angle, 92 degrees is the angle which this resultant force makes with the y-axis. Okay, and then let's talk about gamma. So similarly, we'll take this y component of resultant force, which is 1080 newtons, divided by the magnitude of Fr, which is 1175 newtons, and we'll get 157 degrees, which is the angle gamma, right? With this resultant force makes with the z-axis. Okay, so in this manner, we can find the magnitude of resultant force, or the resultant force vector of any number of forces, and its coordinate angles which it makes with x, y, and z axis. Right? Okay, so that's how we applied the concepts which we learned earlier. Now let's move forward. Let's move on to the next topic. Okay, so the next topic for today is dot product. Right, so what is a dot product? That is the first question, right? What is a dot product? So basically, we are talking about vectors, right? So once we talk about vectors, we have two types of products, right? Dot product and cross product. The main difference between dot product and cross product is that dot product gives you a scalar and cross product gives you a vector, right? So the resultant of dot product is a scalar, just a number, right? And the resultant of cross product is a vector quantity. It's not a scalar, right? So that's the main difference, but let's focus on dot product for now, because in this chapter we are talking about dot product. Next chapter we'll talk about cross product. Okay. All right. So let's talk about dot product. Why do we do the dot product? Right. To determine the angle between two vectors. All right. And also determine the projection of a vector along a specified line. Right. So previously we were talking about a force vector along a line. Now we are talking about projection of a vector along a line. Okay, so these two are a little different. Okay, we need to understand the concept, okay? And then we'll apply this on a couple of problems so that we can understand more this concept and how to apply this concept. Okay, all right. So let's talk about dot product. All right. Let's see here. Okay, this is a good example, right? So there's a pipe wrench, right? I think most of us have used this or some kind of wrench, right? So what is this man doing? He is using his hand. He's pulling this wrench with some force, with the force of 80 newtons, right, in some direction. Okay, and trying to turn the bolt. Okay, so now the question is, he's applying the force in this direction, right? Let's say this direction. Okay, he's applying the force in this direction. Okay, now the question is this like the whole force applied by this man is turning this wrench or no? The answer is no, right? Because this force is at some angle to the line perpendicular to AB, right? Okay, so there is some part of this force which is basically turning this wrench, right? Now let's come back to the statement which is written here. For the force F applied to the wrench at point A, this is point A, right, where the force is being applied. What component of it actually helps turn the bolt? Right, same thing what we discussed, right? The force component acting perpendicular to the arm AB of the pipe. So this is arm AB, right? Now perpendicular to this is, let's say, this direction in 3 dimensions, right? Okay. So only this force, this guy, is responsible for turning the wrench, right? But not the whole force of 80 newtons. So how will we find the component of a force, which we sometimes call projection of a force along this line, right? Along this line. Okay, so that we'll see here. Okay, all right. So now let's focus on dot product. Okay, let's say we have two vectors. We can only do the product once we have two vectors, right? So similar, same case for dot product and same case for cross product. But again, let's focus for now on dot product. So let's say we have a vector A we have a vector B with some angle theta in between them, right? So the dot product of vector A and vector B is defined as this guy, A dot B, right? Since it's a dot product, so we use this dot between A and B to represent the dot product. And how do we find it? A times B times cosine of theta. This gives us the dot product of vector A and vector B. Angle theta is the angle between the two vectors, right? It's already shown on the figure. Okay, so this is the dot product. Let's go in more details. What are the dot product characteristics? We already talked about these. The result of the dot product is a scalar, right? So it's just a number. Okay, there's no direction. It's not a vector. Right? So A times B times cosine theta will give you a scalar. The units of dot product will be the product of the units of A and B vectors, right? So since we are doing A times B, so the units will also be A times B, right? Or unit A times unit B, we can say that. Okay, so these were some of the details about dot product. Now let's talk about dot product a little more. So before we jump onto this, let's talk about this. Let's talk about this. Okay, we know that these are the unit vectors I, J, and K, right? I, we know that it's along x-axis, so 1, 0, 0 is the coordinates of I, right? And J is 0, 1, 0, K is 0, 0, 1, since it's for z-axis. Now with this, you can say that I dot I, J dot J, and K dot K equals 1, right? You can just try and solve these. I dot I, J dot J, or K dot K, you'll get a unity, you'll get 1. Whereas if you do I dot J, or J dot K, or I dot K, you'll get a 0, right? So that's one thing which we need to remember. Okay, now let's come here. Let's come back to the dot product. So A dot B, we have two vectors, vector A and vector B, and we are doing a dot product between vector A and vector B, right? So we the vector A is this guy, AXI plus AYJ plus AZK, right? And we are doing the dot product with vector B, which is BXI plus BYJ plus BZK, right? 3 components of vector A, 3 components of vector B, along with I, J, and K, right? So now if you multiply these two vectors, we'll get this. Using these, right? We need to use these I dot J type things to find out this A dot B, right? So what we will get for A dot B, we'll get AX times BX plus AY times BY plus AZ times BZ, right? So again, it will give you a scalar quantity. So it will just be a number with no direction because it's not a vector. Okay, so this is the details of dot product. How do you get the dot product? A dot B. Okay. All right. So now, how do we find the angle between the two vectors using the dot product? Okay. So again, we have these two vectors, vector A and vector B, with this angle theta between them, right? So for these two vectors in Cartesian form, how do we find the angle? We have these two vectors, so we can find out the dot product of these two vectors, right? So we can do this dot product A dot B, which is AX times BX plus AY times BY plus AZ times BZ, right? So we'll get a scalar, get a number. Then find the magnitudes AB of the vectors A and B, right? And use the definition of dot product and solve for theta. Okay, so just rearrange the equation for dot product, and you can find theta equals cosine inverse A dot B divided by AB, right? So once you do that, then you can find out the angle theta, which is between 0 and 180 degrees, right? Okay, so that's how you use this dot product to find the angle between two vectors. All right, okay. Now, as we discussed during the initial part of this lecture about the application of dot product or application of projection of a vector, right? So let's find out how to determine the projection of a vector. Okay, so if you look in this figure, so we have this vector A, right? Vector A in this direction. This is your vector A. Okay, and this is your line AA. Line AA, or we can say axis AA, right? So this is your line AA. Okay, so how do we find the projection of a vector along this line AA, right? So that's a question. How do we do that? So you can determine the components of a vector parallel and perpendicular to a line using the dot product. Okay, so the projection of this vector A parallel to line AA will be A sub A. Right? And perpendicular to this line will be shown like this, A and perpendicular side. Okay, so that's how you do it. Okay, now let's see the steps. Okay, which steps do we follow to do such kind of analysis? Okay, first of all, we need to find the unit vector U sub A along line AA. So this is U sub A, which is the unit vector along line AA. Okay, so we'll find out this unit vector, then find the scalar projection of vector A along line AA, right, by using this. Okay, so we denote this, we represent this by A and a parallel sign, so A parallel, which equals A dot U sub A, right? So a dot product between a vector A and the unit vector along that line, so U sub A, right? And we know how to get the dot product, so we'll get this AX times UX, AY times UY plus AZ times UZ. So this will give us the component of that force or component of that vector along line AA or parallel to line AA. All right, okay. Now, if required, the projection can be written as a vector A parallel by using the unit vector U sub A and the magnitude found in the step 2. Okay, so if you want to find the parallel vector in vector form, then we can do this. A parallel equals A parallel, which is the scalar, times U sub A. So this will give us the parallel component in vector form. All right. Okay. Now we talked about the parallel component. Now let's talk about the perpendicular component. Okay. So perpendicular component can be obtained in this fashion. We know that we use this sign to show the perpendicular component. So A and perpendicular sign equals A square minus A parallel square whole square root. Right, so that's how we can find the A perpendicular in scalar form. Now, to find out the same in vector form, we use this. A perpendicular equals A minus A parallel. Okay. So this will give us the perpendicular projection or perpendicular component in vector form. Okay. All right. So that was the end of the theory portion. Now we can find out, we can apply these concepts on a couple of problems. All right, so let's move ahead. Okay, so example 1. So let's see, what do we have here? Okay, so this is again a 3D system with this hook here. So we have a hook at this point. Okay, we have x-axis here, we have y-axis here, we have z-axis here. All right, and we have a force F which is being applied at point A, right? Shown with this black arrow. Okay, all right, and then we have this line AO. Okay, all right. So what is given? The force acting on the hook at point A. So the force acting on the hook at point A. Okay, what do we need to find? We need to find the angle between the force vector and line AO. Okay, so we need to find the angle between the force vector and line AO, which is shown by this angle theta here, right? Okay, and also the magnitude of projection of the force along line AO. All right, okay, so we need to determine these two things. Okay, the angle theta and the projection of the force along line AO. Okay, so we just discussed how we do that. So let's do this here. Okay, all right, so what are the steps we should follow for such problems? First of all, we know that we are solving for the angle between force F, force vector, and the line AO. So we need position vector RAO, right? Okay, so let's find out position vector RAO, and then we can find angle theta, right? So then we can find angle theta with this equation. Theta equals cosine inverse the vector dot product of F and RAO divided by the product of the magnitudes of F and RAO. Okay, so this will give us the angle theta. All right, next step, we'll find the projection of this force F along line AO, right? So we can use this to find out the projection of that force along line AO, right? So we'll find out F sub AO equals the force vector F dot product with UAO, unit vector AO, or we can just do F cosine theta, right? If we know the force F, and if we know the angle theta, which we have found in the second step, so we can just do F cosine theta and we will find FAO. Okay, all right, so now let's do it. Okay, so we have the geometry, x-axis, y-axis, z-axis, right? This is your point A. Okay, this hook is your point A. We have a force here, this force F. Okay, and let's find out this angle theta. Okay, find out angle theta, we need to find out RAO. Okay, so position vector RAO. I think we have done enough practice on finding out the position vector, and you'll do more practice in your homework. So this is the same thing, right? Finding out the position vector, applying tip minus tail rule, tip to tail rule. Okay, so here, as we are doing RAO, so O is the tip and A is the tail, right? So we'll do O minus A, right? So once we do XO minus XA, we'll get negative 1I. Once we do YO minus YA, we'll get a positive 2J. And once we do ZO minus ZA, we'll get a negative 2 times K, right? So we'll get RAO as this guy. Negative 1I plus 2J minus 2K, and of course, the units, meters. Okay, so after we have this RAO, which is the position vector from point A to point O, we'll find out the magnitude of this position vector. Okay, so let's find out the magnitude of this position vector. So this is the magnitude of position vector RAO. Okay, so we'll just do x squared plus y squared plus z squared whole square root. This will give us 3 meters as the magnitude of position vector. Okay. All right. So now we have the position vector and magnitude of position vector, right? And we already have the force vector, right? Negative 6I plus 9J. Sorry. So we already have the position vector F, which equals negative 6I plus 9J plus 3K, right? And it's given in kilonewtons, right? Okay. So once we have this force vector F, we can find the magnitude of this force vector F, right? So let's say the magnitude of this force vector. Okay, x squared plus y squared plus z squared whole square root. We'll do that to get this 11.22 kilonewtons, which is the magnitude of this force. Okay, all right. So once we have this force vector, once we have this RAO, we can find out the dot product between these two vectors, right? So let's do a dot product between F and RAO. Again, Fx times RAOx, Fy times RAOy, and Fz times RAOz. Okay, so negative 6 times negative 1 plus 9 times 2 plus 3 times negative 2. All right, so this will give us 18 kilonewton meter as the dot product between these two vectors. Again, the dot product gives you a scalar, so 18 is a scalar, right? And how about the units? The units of the dot product is the product of the units of both vectors, right? So the force vector, the units was kilonewtons. The position vector, the units was meter. So the dot product will be 18 kilonewton time meter, right? So 18 kilonewton meter is the dot product between these two vectors, F and RAO position vector. All right. Okay. Now we have the dot product. We have the magnitude of F and RAO, so we can find out this angle theta, right? So angle theta will be cosine inverse this dot product divided by this product of the magnitudes, right? So F dot RAO, both vectors, divided by F times RAO, the magnitudes, okay? So we know that this is 18 divided by, we know these values, 11.22 kilonewtons is the magnitude of force F, and 3 meters is the magnitude of position vector. So if you do that, we get 57.67 degrees, which is the angle between these two vectors, right? Between the force vector F and the position vector RAO. All right. So we are up till here. Now let's move forward. Okay. Now next thing was to find out the projection of this force along line AO, right? So we have the position vector, we have the magnitude of position vector. So we can find out the unit vector, U sub AO, right? So we just divide the position vector with the magnitude of position vector. So we'll get this guy, and this is the unit vector, negative 1 by 3i plus 2 by 3j plus negative 2 by 3k. So this is the unit vector U sub AO. Okay, now we can find FAO, right? So let's find FAO, which equals force vector F dot product with UAO, right? So we'll take a dot product. So again, it will be Fx times UAOx plus Fy times UAOy plus Fz times UAOz, right? So negative 6 times negative 1 by 3 plus 9 times 2 by 3 plus 3 times negative 2 by 3. So we'll get 6 kilonewtons as your FAO. And if you remember, we discussed earlier in the lecture that we can just use the dot product equation to find out this FAO also, right? So we can use this FAO equals F times cosine theta, because we already found the angle theta, right? So we can use that equation to find out the magnitude of FAO, right? So 11.22, which is the force F times cosine of 57.67 degrees, right, which is the angle between these two vectors, and we'll again get 6 kilonewtons as FAO. Right? So that way you can check your answer that are we doing right. So once we have these two, 6 kilonewtons, it means that we are working right. Okay, so we have done this problem correctly, and this is a good check. All right, so now let's move over to the last example problem of today's lecture. So let's look at the given system first. Okay, again, we have a 3D problem. So we have x-axis, we have y-axis, we have z-axis. All right, this is your point O, right? And again, we have a pole OA, and there's a force F, 600 pounds, acting at this point A, right? Okay, and there are some dimensions given which you can use to find out the position vectors. Okay, and there are some coordinate angles given also. Okay, so the force acting on the pole at point A, we already said that. What do we need to find? The components of the force acting parallel and perpendicular to the axis of the pole. Okay. So now if you look at this figure, so force is acting in some other direction than the direction of pole OA, right? So we need to find the components of this force acting parallel and perpendicular to the axis of the pole, right? So if you remember, we just discussed during the last part of the lecture how to find the parallel and perpendicular components, right? Okay, so we'll do the same. So what's the plan? What are the steps that we should follow for this problem? Okay, so first of all, first step, find F. Okay, because we are just given the magnitude. F equals 600 pounds. But we need this force in vector form, right? So we'll find out this. Then we find out the position vector ROA, right? Then we'll find the unit vector UOA. All right? Okay. Then determine the parallel component of F using this guy. F parallel equals F times UOA. Dot product between vector F and the position vector, the unit vector UOA, right? So this will give you the F parallel And then we can find out the perpendicular component of force F with this equation. F perpendicular equals F square minus F parallel square whole square root. Okay. All right. So let's move to the solution and let's see how we do it. Okay. So first of all, first thing first, we need the position vector ROA, right? Now we are not going to go into the details of how to find this ROA. Just remember tip to tail rule. So tip minus tail. Okay. A is the tip, O is the tail, right? So A minus O. XA minus XO plus YA minus YO plus ZA minus ZO, right? According to the given geometry. Okay, so we'll get this ROA, which is negative 4I plus 4J plus 2K meters. Okay, so now we have the position vector, so we can find out the magnitude of position vector. So let's find out the position, the magnitude of position vector x squared plus y squared plus z squared whole square root. This will give you 6 meters as the magnitude of position vector. Okay, so now we have the position vector, we have the magnitude of the position vector, so we can find out this guy, right? This guy, which is the unit vector u sub OA. Okay, how do we find unit vector? ROA divided by the magnitude of ROA, right? So if we do that, we get this. Negative 2 by 3I plus 2 by 3J plus 1 by 3K. Right? So this is the unit vector. Now, next thing, we need this force F in vector form, right? It's just given the magnitude, 600 pounds. Right? We need to convert it into vector form. So we need to resolve this force to get X, Y, and Z components, right? This is not X, this is Z. Okay, all right, so we need to resolve this force F. Now, if we look at this force, so if you resolve this force, you cannot get X, Y, and Z components in one step, right? If you remember, we did one problem where we had to do the resolving the force twice, right? So this is also a similar problem, okay? So first we will resolve this force F and we'll get FZ, let's say this guy, we'll get this guy, which is FZ, and we'll get this guy, let's say F dash. Okay, so we'll get this F dash, and then we'll have to do another resolution, and we'll resolve this F dash, and we'll get this guy, which is Fy, and we'll get this guy, which is Fx, right? So this is how we are going to do the resolution of this force F into X, Y, Z component. All right, okay. So let's resolve this force into 3 components, and once we do that, we get this as our force vector F, right? So this is your Fx times I, this is your Fy times J, this is your Fz times K. And of course, pounds is the units. Okay, if you just simplify this, you get this force F here in Cartesian vector form. Okay, negative 150I plus 259.8J plus 519.6K, and of course pounds. Okay, so now you have the position vector ROA, you have the magnitude of position vector ROA, you have the unit vector UOA, and you have the force vector F in vector form. Okay, all right, so now you can just use the concepts which we learned earlier and find the parallel and perpendicular component of force F, right? So first of all, let's find out this F parallel. So F parallel equals this guy, F times UOA, all right? So F times UOA, F, we have the force vector F, and we have the unit vector UOA. Just take the dot product. So F dot UOA, we know how we do it, right? So just the product of X components, Y components, and Z components, right? So this is your force vector F. This is your unit vector UOA. Just take the dot product. So you'll get Fx times UOAX, Fy times UOAY, and Fz times UOAZ. Okay. Once you do that, you get 446 pounds as the F parallel. So this is the component of this force F, which is parallel to this pole OA. Okay. Now you have this force F, which is 600 pounds. You have the F parallel, which is 446 pounds. So you can use this equation to find out the perpendicular component, right? So F perpendicular equals F square minus F parallel square whole square root. Okay. So 600 square minus 446 square whole square root will give us 401 pounds. Okay. So this is how we get the parallel and perpendicular components of a force along a specified line. Okay, so in this case, we had this force F, we had this pole OA, right? So we were required to find the parallel and perpendicular components of this force along this pole OA, right? Okay, so that's how we applied the concept which we learned in today's lecture, and we ended up getting the parallel and perpendicular components of this force F, right? Okay. All right, guys. So this is the end of chapter 2, right? So in the next lecture, we'll start with chapter 3, right? All right. Thank you so much, and see you in the next lecture.